Great. All right, thanks for coming. First about me. So I work at 2 Sigma. It's an investment management company. And I'm an engineering manager there, where my team is responsible for building 2 Sigma's cluster compute environment and distributed analysis platform. I think it's a very large platform, probably tens of thousands of CPUs and petabytes of memory. So we're really working with Spark at a scale that is unique. If you happen to Google me, you'll see I also played in a punk rock band for many years. And this gives me kind of a weird relationship with stages. So I might walk around on the ground or go up. Anyway, I have to read off some legal information. This is a lot of information here, but basically, whatever we present here should not be used to make any investment decisions. It's kind of obvious. I'm going to give toy examples only, but that's the disclaimer. And I may have lifted images from the web that are under fair use, and don't get upset. All right, so 2 Sigma. We're an investment management company, and our mission is to discover value in the world's data and use that value and insights to make informed decisions for our investors. And we're going to focus today on the data part of that mission. So we use a lot of data, and every piece of data we use is a time series. We think of everything as its relationship to time, right? So what is a time series? Very simply, just an ordered sequence of values of a variable. And that variable can be anything we can observe. It can be economic data, like the price of a stock, sensor data, like weather or other data that comes from sensors, or IoT feeds, like what comes from a Fitbit. So we look everywhere we can globally for data and organize that into time series. Time series analysis is the science, or art really, of discovering structure in time series data. The human eye can look at this and immediately see some kind of structure. There's a trend moving upwards. Here is another time series. You can look at this and say, there must be some trend here. Something's happening. Over time, maybe more variance or maybe just more observations. Or seasonality. Again, we can see a trend here. It's easy. But for machines to do this requires time series analysis tools. And for machines to do this across millions of time series, it gets really tough. This is probably the hardest problem in computer science for us right now. So what is time series at 2 Sigma? Well, first of all, we have millions of these time series. A single time series is called a univariate time series. Multivariate time series are groups of time series. We have millions of them. And they're big and small. So a single univariate time series may be 1 gig, but a multivariate time series could be as large as 1 petabyte. We need tools to be able to analyze that. And they can be narrow. You can see a picture of something that has 10 columns. But they can also be very, very wide, ranging in length to even millions of columns. Finally, they can be evenly and unevenly spaced. So you may have very dense data where you have millions of observations coming in a minute, or evenly spaced data that only has 1 observation every 30 minutes. Building a solution that can handle this wide range of time series with a single API is our mission at 2 Sigma, my team's at least.
Great job.
And that's where we come to Flint. So Flint is our time series solution. It's open sourced on github.com/2sigma/Flint. And yesterday, we released the Python bindings for Flint, which we're really excited about, and I'm going to show you today. By the end of the talk, you'll be able to download Flint, install it on your laptop, and kind of play around with the type of analysis we do at 2 Sigma at a much smaller scale. But I think to talk about Flint, I really want to start from the beginning, though, and position our work in Flint in the lineage of Spark and the RDD. So this is the original RDD paper, obviously written by Matei. I think it's the reason why we're all here. And it's amazing to me how this simple abstraction that Matei came up with has launched a conference this large. But it really all comes down to the RDD. RDD is an abstraction that lets us build fault-tolerant distributed programs from a small set of primitives, transforms, and actions. The RDD, it's a multi-set that contains things of type T. And T is an opaque type here, meaning we know nothing about T. And that's important later as we build on this. The transform, this might be a review, but I think it will make sense. So the transform we do with the RDD is flat map. It takes a function that takes as type T and returns a sequence of things of type U. The effect being an RDD of type T is transformed into an RDD of type U. An action, reduce in this case, will materialize an RDD into something of type T. Reduce takes a function which takes two T's and returns a T, having the effect of taking an RDD of type T and materializing that into type T. With these two primitives, we can actually do a wide class of things. We can make fractals. We can generate random numbers. We can do anything that's really embarrassingly parallel. But something's missing here. The RDD paper only got us this far. You can't actually even do word count, the canonical example, with those primitives. You need something to group by. And so the pair RDD is introduced. And the pair RDD takes an RDD, is an RDD that contains tuples, key values, and the important thing is that the key here has an equivalence class. So now you can actually do group by. You can take two things and say, are they the same? And that's a very important property of the key. So K has an equivalence relationship. Now you can do group by key. You can take an RDD, a pair RDD, tuples of KVs, and return an RDD where the values are grouped by key. And you can reduce by key. This is a more efficient operation than group by key and map, where you take a function which takes two V's and returns a V, and takes that pair RDD and returns a new pair RDD where the values are reduced. And now you can do word count. You can also build a database system. You can also build Spark SQL with just these two primitives, glossing over the other transforms there. But this is the core of it. But still, there's something missing. And this missing piece led us to do our work in Flint. Because with pair RDD, we can't do the type of time series analysis we need to do at 2 sigma. Specifically, there's no notion of time. So like we have map and reduce, there are two primitives in time series analysis that are key to, for us to be able to do what we need to do. We need to be able to do windowed aggregations. So if we have a time series along the x-axis there, we need to aggregate values looking back in time. Oh, sorry. And we need to aggregate them by a window. We have windows in Spark SQL, but we need to aggregate them by a window that's defined in time, say the last 5 minutes or the last 5 trading days or business days. Similarly, we need to take column data in our multivariate time series and join these together with some kind of look-back criteria. This is called a temporal join. So a temporal left join takes the table on the left and joins the observations on the right-hand side with a window that can look back some period in time. And just to do those two things, we need another data structure. We need to extend Spark with the time series RDD. And that's our innovation that we released in Flint today. The time series RDD is a pair RDD. That is, there's equivalence class on K, but K also has a natural ordering to it and is defined in a metric space. And by a metric space, we mean that there's the ability to measure the distance between two Ks. Specifically, you can look back 5 seconds or 5 minutes or 5 business days, whatever metric space you want to define. Once we have the time series RDD, we can define the primitives that are going to unlock the potential for the time series analysis we want to do, group by window. So W is a window spec, and the input to the function, which allows us to take the time series RDD and do exactly what we did with the pair RDD, but group this by time according to the window spec. Reduce by window takes a similar function, which takes two V's and returns a V, and the window spec, and returns a time series RDD, where the V's are grouped and reduced by K in the equivalence class for that time. So now we actually have the primitives. We've extended Spark, not in the implementation, but in the paper itself. And we are going to publish our work in a paper here. But we've extended it on first principles, and the implementation of this is Flint. There's a Scala implementation and a Python implementation, and that's on github.com/Flint. All right, now we'll transition to actually using Flint and talk about what you can do with Flint. So Flint, a time series library for Apache Spark. You can go to the README. There's instructions to build it. It's pretty straightforward. You can build the Scala with SBT assembly or the Python. There's a Python folder in there, and you just make this through Python. You can import Flint. There's a Flint context which contains information about your time. And you can see the time series data frame, which is the data frame that you'll operate on. We have a set of summarizers and window functions that perform basic time series analysis functions in Flint. Here's a really simple example. You take Spark. In Spark 2, they introduced a read CSV method, which was really nice. So you can read in a CSV. In practice, we do this in Parquet files that are stored in HDFS, but if you want to get started, read in a CSV. And then I explicitly cast the time column. So in Flint, all the time are nanoseconds since the epoch, and you need to prepare your data ahead of time if you have timestamps to convert that. So here I have a file which has just nanos in it, and I can cast that to long explicitly for that time column. And load 2 data frames. So I've created 2 data frames. They're really simple. This is going to demonstrate this as of join. So on my left-hand side, I have equally spaced observations. On my right-hand side, I have unevenly spaced. And I can now join this data in this temporal join. And just off of the data frame, there's a left join method. I set a tolerance, which is my look-back criteria, which in this case is 1 nanosecond. In practice, this could be very, very large and span multiple partitions. So the complexity of managing partitions across this in Spark is where Flint really provides the scalability. But you can see the time, quote, trade are now aligned. If you look at the first nano, the trade, because there was no table there, contains a look back to the second one. And we've done this temporal join. In practice, this type of join at 2 sigma without Spark and without Flint on very large data sets could take many, many hours. And so with Flint, we're seeing from 10x to even 100x improvement over the tools that we had built prior to this. Another kind of visually assaulting example, but interesting, is the way that our researchers work is very ad hoc in a notebook environment. And they want to iterate through their research by providing their own functions. So we can't possibly provide every function that they'll ever want within Flint. So user-defined functions in Python is how we allow for extending Flint. Here's just a really simple user-defined function. I think we take one price and then subtract another one. It's not anything anyone would actually ever do. User-defined functions can actually become very, very large and complex. But now you can join with the column and apply that function to the data. Also in practice, if you're working with a large data set, you would never call the 2pandas method. But once you've got your work down to a smaller data set that can work in memory, you can call the 2pandas method and bring that into pandas and then work with that to visualize it. So that's a common practice that's done here. There's a talk, I think tomorrow, where Wes is giving, Wes McKinney will talk about the work that we're doing in 2pandas to make that operation much more efficient for even larger data sets. If you go to Flint, there's a Python cookbook that we just published 2 days ago, and it has some 50 different things that you can do with Flint. We're building that cookbook and making that available, and this kind of represents typical things that users might do with Flint, and you can apply to yourself, for yourself. Looking ahead, there's a lot of performance work that we want to do. We're looking towards a data frame API and integration with Catalyst there. Right now we're in the RDD API, as well as improving the performance of serialization of the 2pandas method and user-defined functions. So that's it. That's Flint. You can find me after the talk. I have it running on my laptop. You can play around with it if you want, or talk to me about time series analysis in general. Thanks. I think that was short. So we have time for questions.
So my question is not especially about Spark, but more about investment analytics in general. What data do you use? Because from the outside, the main data is Bloomberg, which costs, I think, 20 grand a year.
Yeah.
So is there no data sources more accessible from outsiders?
Probably not qualified to answer that question. One thing that I like about 2 Sigma is there's a decoupling between the technology stack and the finance side. So I actually feel like I work at a technology company more than a finance company. When I play around with data, I probably grab the same data. I grab Yahoo Finance data or something like that. But the kind of the practice and the business of collecting data is everything in the finance industry. So it's an art. Yeah.
Hi, Dan. How do you figure out the tolerance that you need to specify when you're joining two time series?
So that's user defined. The user is going to decide how far they want to look back based on the type of work they're doing. If you imagine you're doing a window function where you want to calculate some kind of moving average, you're going to define basically the length of that window or that tolerance by how much data you want in your moving average. So that's why it needs to be a window spec that's specified by the user. Similarly, if you're joining two columns, you want to know how far you want to look back on the right-hand side based on whatever use case you have or the data you're preparing.
Let's say you're analyzing completely two different stocks. One is sticking once a day, and another one is sticking 10 times.
Oh, yeah, sorry. So he says, what if you're analyzing two different time series that are unevenly spaced, and one has, say, observations every 30 seconds, and one has observations every 1 second, right? Is that the question? So you would pick your tolerance to include, I would pick 30 seconds there so that you can look back on the, yeah. So the left-hand side would take all the 30 observations on the right-hand side. But it's a matter of like what you want it to do. You could pick 10 seconds and look back 10 seconds. It's really up to the user.
Is it optimized if I pick the whole day, say I pick 24 hours, is it optimized as soon as it finds a point on both, and it goes forward that way?
Yeah, so he asks, is the matching or is the tolerance optimized? So that's the implementation of Flint. And Flint stores metadata about the partitions and the windows so that we can do these kind of joins efficiently, even if the window size is very, very large. If you did this naively and did time as a group by, the shuffle cost that would be incurred if you wanted to collect observations within a window across multiple partitions just kills the performance in the implementation. So you need to optimize for kind of data-aware partitions with the size of the window.
Hi. What is the project status of Flint? Is it used in production in Sigma assets, or is actually a clean up version of some kind of 2 Sigma production code?
Sure. The question is Flint used in production at 2 Sigma? So Flint is used in production at 2 Sigma, and the user-defined functions that we provide in Flint are kind of examples of what someone might do. The proprietary or the intellectual property that we have is not released, obviously, outside, but that's in the form of user-defined functions or libraries that extend Flint internally. But a lot of the core transforms and actions that we do are actually in Flint. These are kind of well-known techniques that have deep prior art, so we're not really concerned with releasing those to the open source. We think that the benefit of developing the software in the Spark community far outweighs keeping them internally. So open source is really important to 2 Sigma in that respect, and that's why we are willing to, or we are encouraged to put stuff out there.
A more generalized question, are you guys using any kind of specialized database such as time series DB or any other database?
The question, are we using a specialized time series database? So 2 Sigma is a big company. There's a lot of technology used, but in my team, Spark is really the core of what we do, and representing data in files in Parquet on HDFS, and then doing the analytics in Spark is the dominant pattern.
So a question. I'm just wondering, how is it different from Spark structured streaming? So they also do like the windowed, stuff. And here, I mean, do you have just one window kind of that you can define, or can you like collect data into multiple windows going back in time for quite a long time?
Yeah, so I think the question is, I'm going to pull back a slide to answer that question. So first of all our work is done on bounded data. So this is not a streaming solution in our case. The way research works is you pick a start time and an end time and do your research on that bounded data. But the question, how is this different than basically what's available in the windowed functions in Spark? SQL, I guess, it would be the answer. So in Spark 1.6, there are window functions, but The window cannot be defined by time. It's just the number of rows that you want to look back. So that doesn't let us do things like 5 seconds or 5 minutes. There's no notion of time. Time is introduced in 2.0, but that requires you to have a partition specification, so you still need to partition your data. And if you look, we can have up to 1 million columns in what we call very wide panel data. So the solution, we just can't afford to partition that way. We might need to have a very small window in time that contains millions of observations in width. And to your other point, how big do window sizes get? You can see window sizes as long as 1 year back, where you want to keep a moving average of data that goes back 1 year. So in that case, when the window size is that big, we really need to be partition aware, and the cost of shuffles in that case with Spark SQL would be prohibitive. Yeah. Thanks.
Are you aware of any use case where Flint is used in, say, high-frequency trading or just trading strategies in general?
Yeah. So Flint was designed with that use case in mind, specifically this evenly and unevenly spaced observations, where in high frequency you can have many, many observations in a very small window, but you may want to join that to data that's coming in on another side at intervals that are 1 second or 30 seconds. So again, the Spark SQL native solution couldn't be used for that high frequency use case, but Flint can stand up to much higher frequency data. Yep.
You can only go back for 1 year in terms of the window size.
Yep.
For high frequency trading, if the number of bars is only, say, 365 or 250, that might be too small. Are you going to address that issue in the near future?
Oh,
Thank
sorry,
you.
I meant that as, that's not a hard limit. You could go back further than that. It's just that's what I think of as a very large window. That would only, so there's no limitation on Flint of how far the window could look back. Yeah, so try it.
I have a question. How do you figure out the partitions for Parquet files?
The partition size?
I guess I'm asking, like, how do you lay out the data? If you look at the stock market, right, you're analyzing, let's say, a Russell 3000 universe for the last 10 years of the tick data and quote data. How do you lay out your trades and quotes and all the different symbols in Parquet files?
Right. So the question is, how do you represent economic data or price data in Parquet files? That is also a dark art, which I probably couldn't cover here. The way that you represent that data in disk is going to directly affect the performance and how you read it. And so there's a very large team at 2 Sigma that is responsible for kind of collecting and organizing that data, but that actually is considered some of our intellectual property. So the examples I have here are pretty naive, but there's ways to do that that are optimal.
Thanks for all this work. This is pretty incredible. There's also a Spark time series package. I think that was on their document on the Spark packages website.
Yep.
And then that's unrelated or is
So,
related?
I know a lot about that, one. Part of the reason why I structured this talk in kind of the RDD and trying to root it in the lineage of that was so that you could have some sense for how to compare different implementations. And the Spark time series is effective, but if you look at the wide range of things that we want to solve here, they make some assumptions that make that solution not applicable to ours. Specifically, they partition things into univariate time series, where we need to work with multivariate time series that can be very, very wide. I think they also assume that observations need to be evenly spaced, and we can't make that assumption. So if you take those 2 assumptions, the Spark series or Spark time series solution wouldn't be useful for us in that capacity.
So just to follow up to that then.
But there is a talk right after this, I think.
On that package?
Yeah, on that
Okay.
package.
Have you been able to implement the statistical models that they're also looking at, like ARIMA, like GARCH?
Yeah, so I don't know if I have I thought I had a slide. So that's another thing. Our focus isn't actually to provide like implementations of specific techniques. It's more to provide the library on which you can build those techniques. Do I have that example? I don't. I had a slide which has a much more complicated UDF where it does something like an ARIMA function. But that isn't, our intention isn't to release that. It's more to provide the tools on which you could build that and then contribute that in your own way. So that's also, I think, a third key difference there. Cool.
Okay, if there are no more questions, that's the end of this talk. The next talk begins at 11:40.
All right, thank you.